Okay, well, welcome everybody to the May meeting of the Mornington Peninsula Astronomical Society, and half the crowd is outside, and more hopefully will come brave the weather for tonight. As we begin, as you can see, there's been some ambient background noise being played, and what this is a project that NASA has been running now for a year or so to turn some of their images into sounds based on, in the particular case that you're listening to, that's actually the sound of M87, which is the first galaxy that a couple of years ago had the black hole imaging that was published, M87. And they're showing there the X-ray, optical and infrared images, and they're digitising it as it sweeps across, so that this is intended for appreciating photographs in another manner, and also for people who are poor of vision as well, so they can appreciate some of the sound. So they've been systematically digitising some of their photographs, particularly in the multi-wavelengths there. So that one's M87. Now, before I get on to the Milky Way one, which is on the one on the right-hand side, down the bottom left there, you would have seen during the month the capture of a re-entering rocket off New Zealand by New Zealand's Rocket Lab company. The picture shown there is the top view of the helicopter's rotors turning round, and then you see this little bob there, which is like a drove parachute on the back of the main parachute, and then the main parachute below, and hanging vertically downwards is the incoming electron rocket. Now, this image here is, this picture here is actually of the test run that they did, whereby they took one up and dropped it from a second helicopter and then attempted to catch it with another one. Because the actual live one, where the rocket came in from orbit after launching about 30-odd new satellites into orbit, while the helicopter actually did successfully snag it with its hook. And the idea of the hook is they come in, they hook a line that's between the drone parachute and the main parachute and sort of snare that. So the helicopter on the live one came in, grabbed it, but then they had to let it go because it wasn't flying very well in the conditions. So just something unusual to risk the life of pilots catching an incoming rocket motor, so it can be reused again. Now, over on the top side, we'll go into the sound of the Milky Way now. We all sit cross-legged on the floor going Om. A little bit of meditative music from NASA. Sagittarius A star, the black hole at the centre of our galaxy, is inside that bright region on the lower right-hand side of the image. And you'll see as it approaches it that if you look at the waveform that's slowly sweeping from left to right, as it goes over Sagittarius A star, you'll see it will go up to a bit of a crescendo, and you'll notice that there any moment it's starting to build as it goes over. Now, this is not any of the images from the Event Horizon telescope. They're yet to actually digitise those in a similar sort of way, so that's something for the future. The image going on in the bottom right-hand side there is zooming into the Milky Way right down to the point of Sagittarius A star. So if you've been looking at the right-hand side, if you follow the arrow, it's pointing as to where Sagittarius A star, the black hole, is in the middle, and it will zoom around in a moment. There we are. So there it is in the Milky Way, and we're slowly zooming our way in to where it is, right down to the point of where optical telescopes and the infrared telescopes can't penetrate any further. Because of course the one that was recently announced is at a different wavelength. I think it's around the millimetre wavelength, so you're getting on for microwave region. And you see here how zooming into the other space telescope images that were actually released about this time last year. shows you it's a pretty dense star field towards the centre of the Milky Way. As you zoom out in, you'll get down to the immediate stars in orbit around the black hole. And then they show the actual motions detected of those stars. So you see that one star is orbiting very close to the point of the arrow there, and another one is flashing underneath it. And that flash is the position of the black hole itself. See that one sort of winking every now and again. Well, enough of that for the moment. Another thing happened during the month was the James Webb Telescope released its first high-resolution image of the Large Magellanic Cloud, shown in the bottom right-hand side. Comparison on the left-hand side is the Spitzer Space Telescope in the infrared, and then the James Webb Telescope out at the Lagrange point L2 on the right-hand side. So considerable improvement in the infrared at infrared wavelengths, and as you see they've got it all aligned up now. So welcome everybody, if there's any new members here or visitors. As usual, I'll go through the events of the past month and up and coming months. Then I'll go into a video about the building blocks of the universe. So this is given by Professor Phiala Shanahan. She's actually graduated from Adelaide University and is now at Massachusetts Institute of Technology. And this is a public lecture that she gave all about fundamental building blocks of the universe. We'll get down into subatomic particles and we'll come away with a brilliant understanding of that. Then we'll move on to Mark Stevens' Sky for the Month, have a bit of a break, and then after the break we'll come back to two videos all about the black hole discovery specifically. So these ones have been released in the last couple of days only, and they are particularly good ones. First one is by a well-known online astrophysicist, Becky Smethurst from Oxford University. And why I show two of them is they show you different information in them. So they bring different perspectives to what the black hole image is and what it means and what you can deduce from it. And then the second one, Dr. Derek Muller, we've shown a few videos over the years from him, and he's very good as a science educator. And then at the end we'll close with another short musical video from the Event Horizon Telescope team. Now, recent events. So on the 22nd of April we had the rovers here at the Briars, and I had to pull out at the last moment due to COVID close contact, and Mark Stevens kindly stepped in to talk to the rovers. 23rd of April was a working bee here, and also had the second online day of the National Australian Convention of Amateur Astronomers that was hosted by the ASV over 2 Saturdays in a row. Then we had a committee meeting on the 27th of April by online, and we were talking about the upcoming festival, which I'll talk about in a moment, and also the ventilation in this room to try and keep things as safe as we possibly can, and also the fact that the council is putting in some lighting in the Briars, and to discuss about the negotiations over the lighting there. So it was quite an interesting committee meeting, the last one, and I'm sure the next one will be similarly. Then on the 30th of April we all went to the Into the Wilderness Festival down at Balnarring, which is part of an 11-day event that the Shire was running effectively for the arts and tourist industry. And the day that we were on was actually at Balnarring Racecourse, shown here. As you can see the finishing posts just there, and a couple of kids actually running along past the finishing post, just like a couple of small horses. And we were set up just to the side. We ended up with 6,000 people for the day, was the official count, so quite a lot. And as you can see from the conditions there, it was a bit cloudy in the evening, but it cleared up quite nicely as it darkened. So during the daytime it started off cloudy, but and even a bit drizzly, but then it improved significantly, and we had solar telescopes out there as well. And what I'll do is, if you hold on to your seats, I'll see if I can pan around so you get a good good image of what we're seeing there. So you see there's a marquee on the left and telescope set out all the way around there, and the car park was over to the right hand side. On the 6th of May we had a public night at the Briars, and Catherine McCoy gave the talk there. It's been a while since she's been here. She's been offline for a while, so it was excellent to see her back and talking to the group. Unfortunately that evening was completely clouded over, so they didn't really get to see anything through the night sky, so I suspect that we'll get a few of them coming back this coming public month as well. And on the 10th of May, I spoke to the Langwarrin Christian cadets here at the Briars, and they seemed to enjoy the evening. They got to see a bit of viewing outside. They had to break the meeting part the way through as cloud was starting to come in, but they at least got to see something in the night sky. And there's some more images shown there. The one on the left is mine, and the two on the right from Merida. And that shows the back and the front of the marquee. You see great big, on the bottom right hand one there, you see the big pole towards the south, so that's obviously the South Pole. And you see fairly busy collection inside of the marquee. So we had a television set up there on a stand that Greg kindly welded together for the event, and which hopefully we can put to good use here as well. And they're strung up various posters inside, and Trevor, which you see in the bottom left image there, in the middle, he spent hours on his feet explaining his meteorites, and indeed he even had a dinosaur egg with him as well to the public who was coming and going as the day progressed. So all in all, a great sort of day, and we certainly would have reached a lot of people. Now, whether or not we see them as members or that up at the Briars remains to be seen, but we certainly gave out a lot of information there, and also a fair amount of information about light pollution as well. There were displays on as well that aren't actually shown in that image. So coming up in the next month, we've got a working bee and barbecue, I assume, this Saturday here at the Briars at the usual time of 4 p.m. If for some reason that is called off, maybe because of atrocious weather or that, it will be put out on eScorpia, so keep an eye on your emails. Next committee meeting is next Wednesday by Zoom. Then the next public stargazing night is here, where Manfred is going to be giving the talk to the public, which is good. It's been a while since he's been able to come here to the Briars as well, so good to see Catherine back and Manfred back as well talking. Then a week later we've got the quarterly Scouts, Guides and Cubs night here at the Briars, and Manfred has also offered to talk to that one as well. Then the day after we're either out at Narrowarren for the Narrowarren South Scouts or at Cranbourne. They're yet to actually tell us the location. I believe they're having some issues with their hall when they originally booked this in. So we're going to be at one or the other on that particular Saturday. Then the next monthly meeting is middle of June, and another one that's just slipped on to the calendar is in November. We're up at Bentley again for the Bentley Festival, and the application for that is in, and on the assumption that they allow us in, because of course they still actually have COVID rules into place. So in other words, they still require vaccination from anyone who's going to be there, and all the usual COVID rules that don't seem to apply to anyone else anymore. The local council up there seems to be actually requiring it still. So that's the items coming up. So tonight's talk is by this young lady, Assistant Professor Phiala Shanahan, and she's actually giving a public lecture here in a Canadian Institute for Theoretical Physics, and she'll talk about the fundamental building blocks of the universe. This goes for about 3/4 of an hour or so, including a couple of questions at the end. And then after that we'll go into Mark's sky for the month. So on the assumption that you can hear this okay.
Thank you very much. It's an absolute delight to be here today to talk about one of the fundamental, even defining questions for physics. What is everything made of? Debate about this topic, recorded debate, goes back to 500 or 600 years BC. And of course, scientific thought has progressed a lot since then, but trying to answer this question, what are the fundamental building blocks of the universe, is still driving the frontiers of physics forward today. We understand that matter is made of atoms. Atoms are inconceivably tiny. If you imagine walking along your favorite beach, there are more atoms in a single grain of sand than the number of grains of sand on that beach. Despite the name atom, which means indivisible, atoms have substructure. At their core is a densely packed nucleus of protons and neutrons, orbited by a cloud of electrons. We understand that the structure of atoms actually goes one level deeper. Protons and neutrons themselves are made of more fundamental particles, matter particles called quarks, held glued tightly together by force-carrying particles that embody the strong nuclear force called gluons. As far as we know, that's it. There's no deeper levels of structure to be found. Quarks and gluons are fundamental building blocks of the universe. Of course, it would be a very exciting day for science if we found out that that's not the case. Quarks and gluons and their interactions are described by what's known as the standard model of particle physics, or the standard model of elementary particles. There are 17 fundamental particles, 6 different types or flavors of quarks called up, down, charm, strange, top and bottom. Particles called leptons, which include the electron and the electron neutrino, as well as heavier copies of those called the muon and the tau. 4 force-carrying particles, the gluon that we've already heard about for the strong interactions, the photon for electromagnetic interactions, and the W and Z bosons, which carry the weak force, and the Higgs boson. This theory was written down in the 1970s, but it wasn't until more recently that all of these particles were actually found experimentally in accelerators. The W and Z boson in 1983, the top quark in 1995, the tau neutrino, most recently in 2000, and then an event I'm sure many of you would remember, the Higgs boson, was the last piece of this puzzle to be found experimentally at the Large Hadron Collider in 2012. The standard model describes 3 of the 4 fundamental forces that we know of in nature. Electromagnetism, that's what binds the positively charged nucleus of an atom with the negatively charged electrons. The strong nuclear force, that's the force that overcomes the repulsion of 2 positively charged protons to bind them into an atomic nucleus. The weak nuclear force, which is responsible for beta decay, the conversion of a proton to a neutron, the decay of that proton. What's not included is gravity. Gravity is described by a different theory of general relativity, and trying to unite these 2 frameworks into one unified theory is still a grand challenge in physics. The equations that describe the standard model, these 17 fundamental particles and their interactions, are beautifully and wonderfully, alluringly concise. You can fit them on your coffee cup. Yet, to the best of our understanding, this theory describes the strong electromagnetic and weak interactions at all distance scales. From the internal dynamics of quarks and gluons in the inside of a proton, to the way protons and neutrons come together to form atomic nuclei and the elements in the periodic table, through to the nuclear reactions that happen in the burning of the sun, the conversion of hydrogen to helium that emits light that we see as sunlight here on Earth, to nuclear reactions that we see here on Earth, for example, to generate energy or for medicine. And even up to the cosmic scale, this theory describes the dynamics in the inside of a neutron star, the most densely packed objects in the universe that we know about. So I study the standard model of elementary particles, and there are really 2 motivations for this. First, I want to understand how the universe is built from these 17 fundamental building blocks, see the complexities of nuclear physics emerge from this theory. And secondly, We want to understand new physics beyond the standard model. But to do that, we need to know standard model backgrounds, benchmarks. We have to understand the standard model to find where it breaks down, to learn new things about the universe. Although the theory is so elegant, I still can't sit down and calculate something that I might like to know by hand from the standard model. Let's say the mass of the proton. We just don't know how to do the maths, how to solve those equations. What we can do is to put the theory onto a computer. Essentially, we discretize the theory, put it onto a four-dimensional space-time grid. That's 3 dimensions for space and 1 for time. And in that formulation, we can calculate things from the theory, like the mass of the proton, on a computer. Now, these computations are extraordinarily demanding. Some of the calculations that I'll discuss, if you were to put them on a fairly good laptop or desktop computer that you might have at home, would take 10,000 years to complete. Of course, that's not what we do. I use the most powerful supercomputers in the world. Just to give you an idea of the scale of this computation, the biggest supercomputer in the world at the moment is known as Summit. It's at Oak Ridge National Laboratory in the US. It's a physically large machine. Here's a person for scale. And computationally, this machine is huge. The Summit supercomputer can do in 1 second what it would take the entire population of the world a year to do if everyone did one calculation every second for the entirety of that year. This is an enormous amount of computational power. And we can use that computational power to understand the universe from its fundamental building blocks. Starting at the smallest scales, the structure inside a proton. What we learn from the standard model is that the building blocks of the universe are not at all like Lego blocks. The simplest description of a proton has 3 quarks held glued tightly together by gluons. But what we see is that as you probe the structure of the proton at higher and higher energy scales, a more complicated dynamical structure emerges. Quark and antiquark pairs, antiquarks are the antimatter particles that correspond to quarks, can emerge out of empty space, out of what we call the quantum vacuum, and then annihilate again. And what you see is a bubbling, boiling, dynamical, complicated structure on the inside of the proton. But we can study this structure to understand some of the fundamental things about our universe. For example, we see in an experiment that the neutron is just ever so slightly heavier than the proton, by about 0.1%. That small difference is absolutely essential for life as we know it. The proton is the nucleus of the hydrogen atom, and it's that attraction between the positively charged proton and the negatively charged electrons that holds it together. If we were to suddenly reverse the mass difference of the proton and neutron, so the proton's now heavier, the proton could decay. Without those electrostatic forces to bind them, matter would collapse into black holes or into neutron stars, and we wouldn't be here to ask these questions. What we can measure experimentally is that there is this very small mass difference between the proton and neutron. What we can do from the standard model is understand it in terms of the fundamental constituents. This is very recent work. Just from the last few years, we were able to calculate the mass difference between the proton and neutron. The experimental number is shown here in orange, from the standard model, and see that this small difference arises from a delicate interplay of the strong and electromagnetic interactions, which push the mass difference in opposite directions and cancel to give us the same number that we observe in nature. So moving from the mass of the proton to another fundamental property about the proton, the pressure generated by the quarks and gluons inside. This is even more recent work. We only released this in the last month. We calculated the pressure distribution inside the proton. So in this figure, over on the left-hand side is close to the center of the proton, and as you move out, you're moving further out from the center towards the outside. We find a positive pressure in the inside, that's a repulsive pressure, and as you move further away, a negative, a confining pressure inside the proton. What's quite remarkable is that the pressure inside the proton at its peak value is greater than the inside of a neutron star, the most dense known objects in the universe. So unlike the proton-neutron mass difference, which we've measured extremely precisely experimentally, this is an example where theory is more precise than the current experiments. We have a prediction to be tested at future experiments. So there really is a synergy and an interplay between theory and experiment as we strive to learn more about the universe. And this is a particularly exciting time for thinking about the structure of the proton. In the next 10 years or so, we expect a new particle collider, an electron-ion collider, to be built in the United States. And this machine is designed precisely to study the internal dynamics inside a proton, and will allow measurements of things like the pressure distribution to a much higher precision than we've ever had before. So we really are looking at a new frontier of understanding of the smallest things in the universe. So moving from the very small up to the more cosmic scale. As I said, we believe the Standard Model describes the strong electromagnetic and weak interactions at all distance scales. So they describe the primordial nuclear reactions that happen in the first moments after the Big Bang. After the Big Bang, the universe was a hot, dense particle soup. As the universe expanded and it cooled, within about the first second, we had protons, neutrons, electrons, photons, neutrinos, and their antiparticles. Then what happened is called Big Bang nucleosynthesis. In the 10 seconds to 20-minute time interval after the Big Bang, those first protons and neutrons combined in chain reactions that formed the very first elements. So here in the first step, protons and neutrons fuse into a deuteron, a two-body state, and then the chain reaction continues. So a few years ago, this first step of this first nuclear chain reaction was studied from the Standard Model for the first time. So we were able to really understand how this reaction emerges from those underlying quark and gluon degrees of freedom. And this was a really exciting achievement. This was the first study of a nuclear reaction from the same theory that describes the internal dynamics of a single proton so well. This is also important because in this reaction, the internal degrees of freedom are really important. It's one of the places where the fact that protons and neutrons have this substructure shows up strongly. So we were able to study this from the Standard Model for the first time. Moving to another important nuclear reaction, the reactions that power the sun. The light and heat we see from the sun comes from the proton-proton fusion chain reaction. Again, at the first stage, protons fuse, and we follow all the way from hydrogen down to helium. And the light emitted on the way of this chain reaction is the sunlight that comes down to us here on Earth. Just last year, we were able to study the first step, again, of this proton-proton fusion chain reaction from the Standard Model of elementary particles. So we really are just at the very beginning of an era of understanding nuclear physics from the ground up, understanding nuclear physics from the interactions of fundamental particles. As I hinted at the start of the talk, the Standard Model isn't everything. There are things about the universe that the Standard Model doesn't explain, but Standard Model calculations are essential for working out exactly what that new and unknown physics in the universe is. For example, gravity. That's described by a different theory, not by the Standard Model, and unifying those is a grand challenge. Neutrinos are massless in the Standard Model, but we see experimentally that neutrinos have mass. There are many theories, many proposed mechanisms for putting neutrino masses into the Standard Model, but working out which is the one that best describes our universe is still an open research question. There's also a matter-antimatter asymmetry in our universe that the Standard Model can't explain. If the Big Bang had produced equal amounts of matter and antimatter, and then all of the evolution had proceeded just by the standard model as we understand it, then there wouldn't be nearly as much matter left in the universe as there is. We are all made of matter. The stars and the planets that we see, that's all matter, not antimatter. The matter and antimatter would have annihilated and there'd be far less left by now. Also, dark matter, which I'll spend a lot of the rest of the talk discussing. By about 1980, it was clear that there's a fundamental problem in our understanding of the universe. That what we understand and what we measure from the universe don't match up. What I have here on the slide is a picture of the Coma cluster. This is a large cluster of galaxies near Earth. And as early as the 1930s, it was noticed that the gravitational attraction needed to hold this cluster together couldn't just come from the luminous matter, the matter that we see. There's not enough. But if there was some type of other matter, something that interacts gravitationally, but that we don't see, something that doesn't emit or absorb light, something dark matter, now that could explain this. Another observation was that the speed, the velocity with which the rotation of a galaxy happens isn't what we'd expect. If you look in this figure, as we move out from the center of the galaxy, the velocities that you expect, the galactic rotation curve from the matter you can see, follows this red line. What you actually observe, however, is quite different. It's like this white line. So again, there's something interacting gravitationally that we can't see. Just one more example. This is a now famous picture of what's known as the bullet cluster. What you see here, it's in false color, is pink areas which show matter that we can see, luminous matter. We see light or we see X-rays. That's matter we can see. And here in the blue, matter that we can infer is there. Matter that's interacting gravitationally that we don't see. And you see there's a clear separation here. So we infer these blue areas using something known as gravitational lensing. That is, that light will bend around a massive object in its way. So if we're here on Earth, receiving light from a distant star, and there's something massive in between, light from that star will bend around that mass to reach us. What we then see, since all we see on Earth is the last direction that light came from, is ghost images, virtual images of the star in the directions from which that light came. You can understand this by thinking about how a mirror works. If you're standing in front of a mirror and you're looking at your toes, what's happening is the light from your toes is bouncing to the mirror and to your eyes, and you see a virtual image of your toes on the other side of the mirror. So it's the same sort of virtual images of stars that we see. What I've shown here on the slide is just these two light rays either side, but you have to imagine this in 3 dimensions. So what you really see are rings. And that's exactly what you see. These are sometimes called Einstein rings. So using this, we can infer if there's mass that we can't see by the bending of light around it. And that's how these images were made. So the bullet cluster is just one example. There's a number of examples where we can see this separation of visible mass and inferred mass. So really, we've deduced the existence of dark matter by accumulating evidence, and dark matter is the best theory that fits the evidence. We've never seen it, we can't. It doesn't emit or absorb light, but we know it has to be there. So just an example of how the dark matter might explain this separation. Even in a simple model where we have 2 galaxies with the same distribution of visible matter and dark matter, and we bring those together, the visible matter, it interacts, it will collide. The dark matter will just sail right on by. And so you can see in this collision of 2 galaxies, even from this very simple starting point of the same distributions, can produce exactly the sort of images that we see by observing the universe. Not only can we infer that dark matter must be there, we can infer exactly how much of it there must be. And it turns out quite a lot, about 5 times as much as ordinary matter. Ordinary matter, that's the matter that makes up you, me, the stars, the planets, everything described by the standard model. Dark matter is about 5 times as much of this universe pi. The rest is dark energy that I won't say too much about, other than, again, we've inferred that dark energy must be there. There's a lot of mass in the universe that's interacting gravitationally. So the expansion of the universe over time should be slowing down, pulled back by that mass. But it's not. The expansion of the universe is accelerating. So dark energy is what we call something that has to be driving that acceleration. So back to dark matter. What do we know about dark matter? Well, of course, it interacts gravitationally. That's how we know it's there. It doesn't interact through electromagnetism. We'd be able to see it. It doesn't interact by the strong force. It doesn't seem to interact with cosmic rays, which are made of protons. Maybe, just maybe, it interacts through the weak nuclear force, which would give us a way to be able to see it and learn more about its properties. So we know really much more about what dark matter is not than about what it is. We know that it's not normal matter. It's not stars, it's not planets, it's not antimatter. It can't be galaxy-sized black holes because of the amount of gravitational lensing we see. And we have many, many theories for what dark matter could be. Maybe it has something to do with supersymmetry, or extra dimensions, or different force carriers, or different types of neutrinos. We have many theories, but we don't know which, if any, are right. All of these theories predict different properties for dark matter. So for example, here is the mass of a dark matter particle, and here is how strongly it interacts with normal matter. And you see that different theories for dark matter fill in different places in this model space. So how do we constrain that model space, rule out proposed theories for dark matter, or rule them in if we see a signal for dark matter? There's 3 different ways we approach this from experiment, using colliders and doing what we call direct detection and indirect detection. Here's a nice way of visualizing what those 3 different approaches mean. DM here in gold stands for dark matter, SM for standard model, or your standard matter particles. Reading this figure from right to left, we have standard model particles collide to create dark matter. That's what we do at colliders. We smash regular matter, standard model particles together, and you hope that maybe you'll create dark matter. That would then escape from your detector, and you would know it's there from some missing energy or missing momentum from your detector. Indirect detection, reading the figure this way, you look out into the universe, and if somewhere in the universe dark matter is annihilating to create standard model particles that we can see, then you'd have an excess somewhere over what you expect, more standard model particles that you can't explain. And then you could deduce some of the properties of dark matter from that indirect detection. Direct detection, reading up or reading down, we build a detector here on Earth. A big vat of nuclei buried deep underground to protect it from other interactions, and you wait for dark matter to hit it. You look for a direct interaction of your dark matter particle with your normal matter. So in this way, we look for what are called WIMPs, weakly interacting massive particles, that will interact with a nucleus in our detector through the weak interaction. There are many limits on WIMPs from existing experiments. So this is the same sort of figure I showed before. Here's the particle mass on the horizontal axis, and here is how strongly that particle interacts with normal matter. Each of these lines comes from an experiment, and they're limits from experiments. Everything above the line, that part of the model space, is ruled out. So making this figure, however, ruling out those parts of the model space, ruling out models for dark matter, relies on theory calculations of how the dark matter would interact with the particles in your detector. Just the sort of calculations that I was describing before that can tell us about the internal dynamics of a proton, or about primordial nuclear reactions that power the sun or in the early universe. So understanding dark matter, again, relies on understanding the standard model. So all of these constraints at this stage assume that when dark matter comes in, it interacts with just a single proton or neutron inside the very large nucleus in your detector. And the interaction of dark matter with that single proton or neutron is something that we calculate using these big computational tools. Just this year, we've done some new calculations for the first time of how a wide class of dark matter particles would interact with multiple nucleons in your detector, multiple protons or neutrons at the same time. And what we found was that these multi-particle interactions are surprisingly large. That means that if we see dark matter at one of these experiments tomorrow, before we can really interpret what it is, we need to do a lot more work to understand the theory. So many dark matter experiments, most of them, use large nuclei. For example, xenon is a commonly used nucleus that has 130 protons and neutrons. So what you measure is how dark matter is interacting with a body made of 130 protons or neutrons. What you know from theory is how your model for dark matter interacts with one, or maybe with two. And we've just shown that the 2 and 3 body pieces are much larger than you'd expect. So going up to 130 is a huge extrapolation. So to really understand what dark matter is if we see it, we need to do much more intense computations again. So I've said that we're really at the beginning of an era of understanding nuclear physics from the Standard Model. We really are just at that beginning. Many of these problems that we'd like to solve, many of these questions that we'd like to answer, are still too expensive computationally, despite the fact that we have the biggest supercomputers in the world. For example, the structure and interactions of larger nuclei from the Standard Model. So far we've studied the 1-body, 2-body, 3-body, 4-body type systems. Dark matter, like I said, dark matter detectors use nuclei with 130 bodies. Neutrino nuclear scattering is an experimental tool that we can use to learn more about neutrinos. Like I said, neutrinos are massless in the Standard Model, but they have mass in nature. So we want to understand those masses. We want to understand the ordering of the masses of the different types of neutrino. Neutrino nuclear scattering experiments also use nuclei in the detector. For example, there's a big experimental program in the United States called DUNE, which uses argon. That's a nucleus made of 40 protons and neutrons in the detector. To use the results of that experiment to really understand neutrinos, we have to understand the nuclear physics of argon. Again, a very large nucleus. Double beta decay is another tool that we can use to try to learn more about neutrinos. Double beta decay is where 2 neutrons decay via beta decay to 2 protons at the same time. And studying this can teach us about neutrinos. But the lightest nuclei that undergo double beta decay are again quite large, with tens of nucleons. So studying this again directly from the Standard Model, as we need to do, is massively computationally challenging. There are even simpler questions still that are too difficult computationally for us to answer right now. And this one, this happened when I was in graduate school, and it's been something that's been of great interest to me ever since. In 2010, we realized that we don't really know the size of the proton. You'd think, like the proton mass, that its radius or the proton size would be something that we know extremely well. But for the last decade, there have been conflicting experimental results for the size of the proton. If you measure the size of the proton from a hydrogen atom, you get something quite different than if you measure the size of the proton using muonic hydrogen. That's a hydrogen atom where instead of an electron, you have its heavier cousin, the muon, in the atom. And that difference is really quite striking. Here you see results from muonic hydrogen. This is the proton radius on the horizontal axis. And over here, you see different experimental results using electronic hydrogen. The width of this band gives you an idea of the uncertainty on the results. And these two bands are very, very many bandwidths apart. Right? They're very different. Is this a sign of new physics? From the standard model, the proton radius should be the same thing no matter how you measure it. We don't know. To find out, what we really want to know is what is the radius of the proton from the standard model, from the fundamental quark and gluon degrees of freedom. And we can calculate that, but the error bar, how uncertain we are about the results, is far larger than the difference between these two experimental measurements. Doing better, being able to differentiate between these two, it will take far more computation than we have available at the moment. So all the way from these complicated nuclear physics questions to really fairly simple ones, like what's the size of the proton, we're still limited by computation. Computers improve, and they improve really, really quickly. It's called Moore's law, that computational power improves essentially exponentially. So for the last decades, every 2 or 3 years has seen a doubling in computational power. The different lines on this figure, this is the sum of the top 500 supercomputers in the world. This is the top 1. This is number 500. You can see all of them are improving exponentially quickly. On this axis, each line is 10 times better than the last line. But that's not enough. If I want to answer these questions in my lifetime, even this exponential increase in computer power won't be enough. So the answer is, of course, to work smarter. Spend a lot of time working on new algorithms, new ways of putting the standard model onto the supercomputers so that we can do these calculations more efficiently with less computational resources. That goes from things like sparse matrix inversion, that's how you deal with matrices, very large arrays of numbers where very many of them are zero. Are there efficient ways of dealing with such matrices? To things like noise optimization. Is there a way of having calculations where each sample doesn't fluctuate as much, so you have a cleaner signal with fewer samples in a well-defined way? To just in the last few years, I've been exploring the applications of machine learning to these sorts of problems. Of course, machine learning has been wildly successful in domains like image recognition, the fact that Google can tell you if your photo is a dog or a cat. So I, of course, don't want to know if my photo is a dog or a cat. I want to study the standard model. And so adapting these sorts of new tools in machine learning and artificial intelligence to these precise physics questions and to the scale of these massive computations is a great task. There are also other opportunities like new options in computation, new computational paradigms like quantum computing, which is still in its very, very early days. But there's a hope that maybe a quantum computer, where instead of binary bits, you have quantum bits storing information, will be exactly the right way to study these complicated quantum systems. So there are different ways to approach using quantum computation for these sorts of problems. The first is start from the ground up. Put your theory of the standard model onto a quantum computer, like we do on classical computers, and do the calculation. Now that is a long, long, long way away. At the moment, the quantum computers we have are small, they're noisy, and putting even simpler theories on them is still a challenge. Another opportunity that I'm exploring is with these first quantum computers, these small, noisy quantum computers, are there parts of my calculation, maybe just a piece, that you could outsource more efficiently to a quantum device? So rather than trying to do the whole calculation from the ground up in a quantum framework, are there just pieces that might accelerate you enough to get over the hump to studying something like complicated nuclear physics from the Standard Model. Another really exciting opportunity is given by FPGAs, that's Field Programmable Gate Array hardware. These are new types of computer chips. And what they allow, as the name suggests, is for you to basically reprogram, reconfigure the chip after it's been produced. That gives us an opportunity to radically tailor a computer to the calculations that you're trying to do. So for example, the calculation of the proton radius. Much like you might build an experiment to measure the proton radius, I want to build a computer to measure, to calculate the proton radius from the Standard Model. A computer so radically tailored in the hardware and in the geometry of its connections to be exactly what I need for this theory calculation, that I can do something that on the biggest supercomputers in the world now, which are generic computers, they're used not just for my calculations, but for all sorts of scientific applications, do something that they couldn't do in the next 50 years. So by doing this, I hope that we might be able to answer some of these questions. For example, what is the proton radius from the Standard Model in the next 5 or 10 years? So with that glimpse towards the future, I want to leave with this picture. So the Standard Model that I've described, it's been an extraordinarily successful theory of the universe. For the last 50 years, this theory has withstood almost every test that we've thrown at it, other than the ones that I mentioned, right? So over that time, we've found that this wonderfully elegant theory describes everything from the internal dynamics of a proton. It can explain why the neutron is heavier than the proton, and through that, why atoms don't just collapse in on themselves if the proton could decay. It can explain the first steps of the first ever nuclear reactions in the moments after the Big Bang. And of course, we want to explain the next steps too from the theory, and that will require more computation again. The Standard Model can explain the chain reactions that power the sun, that give us light and heat here on Earth. And ultimately, what we want to see is, can this theory explain all of nuclear physics? Can we get the periodic table from the Standard Model? And hopefully we can't. Hopefully we'll find places where the theory breaks down that point us again in the right direction, like gravitational interactions not working quite as we expect points us in the direction of dark matter. Hopefully we'll find something that points us towards the new and unknown physics in the universe so that we can build a new Standard Model to understand even more of the universe's structure. Thank you.
So we've got time for questions and answers. There is a microphone right here, and if people just want to come over to the side.
Thanks for a really great talk. I appreciate that. My question is about dark matter. Is it possible to take the piece parts from the Standard Model with a cookbook, put them all together, and in fact come up with something which meets all the criteria, i.e., no electromagnetic interaction, totally neutral, fairly large, that sort of thing? You know what I mean? Or do you need something totally and completely new?
We need something totally and completely new. Yeah.
Hi. Could dark matter possibly be responsible for the asymmetry between the ordinary matter and antimatter?
Yeah, so that's a really good question. Of course, it depends on exactly what dark matter ends up being. And there are, with most theories, no, probably not, but then most theories for dark matter are really quite simple. We say, well, what if dark matter is this particle? But we know that normal matter is extremely complicated. We have these 17 fundamental particles and all of these complicated dynamics that give us nuclear physics, and then we say, well, 5 times as much matter that's dark matter, that's just going to be one thing. Right? So our understanding of dark matter is so limited that it's really hard to answer that question. But that would be great. If someone has a theory that explains dark matter and the asymmetry of the universe at the same time, that would be a great contender for a new theory of the universe.
Thank you.
Leigh Schmittner, before the war, discovered fission. She didn't really believe there was a phenomenon. It was something as a surprise. After the war, obviously it's developed. Do we think we can engineer exotic forms of matter from the new elements we're discovering that might be the solution for the environmental crisis in the future?
So do you mean new forms of standard model matter?
That fission and fusion were a quantum leap to the energy we use today, even though it isn't enough. Can we discover a new level of energy from gluons and quarks and dark matter?
Yeah, so that's a good question as well. I guess the answer is, again, if you think about the fact that we've found ever deeper levels of structure, it's hard to say from the standard model that we know now how that might happen. But what if quarks aren't fundamental particles? What if there's another level of structure again? What if there's a whole level of structure beyond what we currently understand? And that would open doors for whole new processes and a whole new understanding of them, which it would be another quantum leap, as you say. But of course, we don't know if that's the case.
Perhaps.
Well, we've got another gentleman just coming. Let me just do a quick one from our online viewers. What scientific question keeps you up at night? What puzzle do you hope will be solved or hope you will solve during your career?
Yeah, so a puzzle that I hope I will solve during my career would be this question of the proton radius. I mean, is that really a signal of new physics? Is one of the experiments, does that just have a systematic that we don't understand? And this is a key example where I know exactly how to do that calculation. I know exactly what I would do to tell you what the proton radius is from the theory. And then if it agrees with one, maybe that's telling us that new physics is moving the other in the other direction. If it agrees with the other, it tells us something again. Maybe it's right in the middle. Maybe it tells us that both of the experiments have problems. So that's a problem that if someone gives me a big enough computer now or gives me a few $1 million to build a completely custom computer, that's a question I could answer tomorrow. So that's something I want to answer in my career. I guess what keeps me up at night is trying to overcome this exponentially difficult problem of studying larger and larger nuclei. At the moment, without something radical, without quantum computing or these custom computers, we're not going to get there in my career. So trying to come up with something radical to let us get there keeps me up at night.
Can you tell me if any of the 17 basic particles can exist in quantity outside of the proton?
Yeah, sure. So things like photons aren't confined to the proton, right? It's the quarks and gluons are confined, but not just to the proton, to other sorts of particles as well. But for example, neutrinos, photons, the electrons, they can all exist outside of the proton.
So I guess what I'm trying to get at too is in any possibility that quarks, there could be a huge number of quarks creating dark matter that we can't detect because we can't detect quarks by themselves other than in particle accelerators.
Yeah, so the interesting thing about quarks is that they can't actually live on their own. If you take two quarks and you start to pull them further and further apart, eventually what you'll get is they'll come apart, but from the vacuum, quark-antiquark pairs will emerge to give you now two things that are quarks bound together rather than just one. So you can't isolate a quark on its own. It's called confinement. And quarks really can't be dark matter because we know they interact through the strong interaction, and dark matter doesn't.
We have an online question, which I think is from a future Phiala. What advice do you have for a high school girl interested in pursuing theoretical physics as a career?
Fantastic. I would say that theoretical physics is built on mathematics, and nowadays it's built on computer science. So at the level of a high school or beginning university student, you need to build those foundations. You need to understand mathematics, pure mathematics as well as applied mathematics. You need to understand computing nowadays. And you need to be able to put all those pieces together when it comes to doing research in fundamental physics.
Okay. Any other questions on the floor? Well, please, let's thank very much Dr. Phiala Shanahan.
Hi everyone, back in front of you this month instead of having listened to my voice over. And I actually was going through the last month one, I think I actually left out part of it, but not to worry. So welcome to Sky for the Month for May 22. As usual, I'll actually cover the first part of June as well, up until our next meeting. May, June, the full moon is due 2 nights ago. Yeah, 2 nights ago was a full moon, so still got pretty well got most of the moon at the moment, and we're new moon on the 30th, so if I'm wanting to do deep sky photography and actually gets a clear night to do it, we're heading into a new moon phase. Still things to look for. We've got 4 bright planets still in the early morning. There you've still got Venus, Jupiter, Saturn and Mars, and for the really intrepid, Neptune's there as well. So, and in actual fact, on the 18th, which is tonight, Neptune is about half a degree north of Mars. Now, half a degree is the width of your thumb held at arm's length. So you can spot Mars quite easily, and Neptune's very close to it. The interesting thing through a telescope there is one's blue and one's red. So interesting little pairing for colour photography. Comet Kopf. Oh, I don't know why it does that. Comet Kopf is half a degree southeast of Neptune. That's on the 21st. Now Neptune and Mars will part ways a little bit, but Neptune will be still fairly close to Mars, which will help find it. And Comet Kopf, which I'll give a little bit more information on, is about half a degree away from Neptune. So once again, another one for the astrophotographers, a comet and a planet in fairly close proximity. 22nd of the 5th, Mercury is in inferior conjunction, which means it's between us and the Sun. Unfortunately, it's not on a plane such that it'll give us a transit. That's just the unfortunate aspects. They're quite rare. Moving into June, on the 12th of June, Uranus will have gone through its conjunction with the Sun. It'll be about 1.5 degrees north of Venus. So once again, you can use a bright, easy to find planet to maybe find one that is just outside your vision range. Full moon on the 14th. Once again, a supermoon, like 2 supermoons in a row. A few nights ago, the full moon was a supermoon, and if you were in the right part of the planet, you would have got to see the eclipse, Fred.
Yeah, when I told you earlier on, I was looking for that eclipse. Where was the best place to see that eclipse on Monday?
I believe the only place in Australia had any hope of seeing it was Perth. And I don't think they got a full, I think they only got a partial.
I think around the United States is probably the best part.
Yeah, where was that ship that Trevor spoke of? Where was that sailing? A ship named the Eclipse was able to film the eclipse. So there you go. And on the 17th, we've got Mercury at greatest elongation west, meaning it's an AM object. Now, apparently it's going to be a lot more visible just because of the quirks between where it is relative in its orbit to ours. It'll actually be a bit higher above the horizon than it was while it was an evening object. So if anyone want to have a look at a little white dot, go for it. Which pretty well means all the planets are morning objects at the moment, so it's unfortunate. Looking at the night sky at the moment, we'll notice that Orion has pretty well disappeared. Generally, I personally use Orion as my summer constellation guide, and I use Scorpio as my winter one. The reason for that is because Scorpio has that big long round tail. The Milky Way is quite clear for most of the time, and quite a reasonable height in the sky as well. Okay, so you've got the Eta Carina Nebula. A little bit lower down here you've got the Tarantula Nebula, which is actually in another galaxy. And I can't even read that one, but another nebula there, as well as the Wild Duck Cluster. Now, around the tail of Scorpio, you've got a few open clusters as well. And one of the best things to have a look at is Antares, and right next to it is a globular cluster. And you can generally get both Antares and the globular cluster. And I think you were having a go at it last week with the camera, weren't you?
A few weeks ago.
Yeah, I think Ben was as well. And I'm getting, it's quite interesting photos, but they're kind of, the problem is you're getting a reasonably bright red star and a fairly dull cluster, so a little bit of camera trickery required. And for those who are interested, the centre of our galaxy is behind Sagittarius there. Don't bother putting your telescope on it, you won't see the black hole. Even if you could see the black hole, you wouldn't see the black hole. But there is so much dust and other stuff between us and the centre of our galaxy. It just looks a little bit brighter, but you can't really see anything. And looking to the south, looking to the north. Okay, something to have a little bit of a look for those who are interested is this Virgo cluster here. And we've got Virgo in a really good observing position at the moment. Virgo cluster is a cluster of galaxies, and it's part of the our local group of galaxies is part of the Virgo supercluster. So it's also part of our address, you know, Earth, solar system, in the local group, part of the Virgo supercluster. And that's there. There's quite a few galaxies in that area to have a look at. So the planets, as I basically said, those wanting to observe the planets at the moment, you're looking at probably around about 3, 4, 5 o'clock in the morning, if you want to see them. They're all fairly close together, some of them drifting even closer and that sort of stuff. Mercury has been in the western evening sky, but it was very low on the horizon, and that's just in relation to its orbit. Everything essentially orbits sort of on the ecliptic plane, but most planets spend a bit of time above or below it, so just depending on where it was relative to ours, as to whether it skimmed our horizon or goes a little higher. Moves through inferior conjunction on the 22nd, passes between us and the Sun, and then it will start to move out. It moves fairly quickly, so it only takes 22 days to actually move through a quarter of its orbit. And so it heads towards the end of May. It'll be moving towards its greatest elongation and be much more visible apparently, so it's going to cooperate a bit. I'm starting to hate this. Venus, also a morning object. It doesn't take much effort to find Venus. Get up, find the brightest thing that's in the western sky, the western morning sky, and you found Venus. Don't confuse it with Jupiter. Jupiter's just slightly not quite as bright. Early in the month it was very close to Jupiter, but Venus moves a lot faster than Jupiter does. It goes around the Sun in 265 days. Jupiter takes 12 years, so they do tend to part ways a little bit. It's obviously still in the morning sky with Saturn, Mars, Neptune's there. If anyone wants to have a bit of a look for a blue dot, that's about all you'll see with Neptune. And Earth, obviously, well into winter. Normally, the winter skies, if they are clear, are quite good because you don't have any heat aberration. But you do have to put up clouds, rain, nice crystals, and generally rain up. Mars, still is one of the morning bright planets. Had a close encounter tonight and tomorrow night with Neptune. It's actually clear out there at the moment, so but it's not morning, so can't see it anyway. Alright, but if you wanted to get up in the morning and it was clear, you've got two fairly, well, as I said, one's blue, one's red, and they're very close proximity. It then moves towards Jupiter, Mars that is, moves towards Jupiter, and we'll finish up about, slightly less than 1 degree apart, so 2 thumb widths at arm's length. Thin thumb. That's it. Okay, Saturn, Jupiter, follows its close encounter at the beginning of the month. It goes, as I said, moves towards Mars as the month progresses. So we can pretty well talk about all these planets in one because it's all the same part of the sky. Saturn's still giving a good view of its rings, that sort of stuff. Get in now, look at them because they'll disappear in 2025 when we pass through the ring plane. And all you'll see is the planet, you won't see the ring system. The other thing is, it just passed through, a few days ago, passed through its eastern quadranture, which basically means it's got a 90-degree angle between the Sun, Earth and Saturn. And the best part of that is it's the best part to look at the rings, because you get the shadow of the planet across the rings, gives it a much better 3D effect. Uranus, in conjunction on the 5th of May, so it's still hiding in the vicinity of the Sun. You won't be able to see Uranus at the moment. It does reappear in the morning sky with the rest of them later in the month, towards the end of the month. And Neptune's also there, but it's about 8th magnitude, so it is definitely a telescope object. And the problem is with all things like Venus and Jupiter being so bright, they can tend to overshadow something like Jupiter. Looking at the planets, you know, up the top there, Mercury, as it moves through inferior conjunction, we are effectively looking at the back of it. So all we really see is the shadow part. And you'll note with Venus and Mercury, the lid side is on the opposite sides. That's because at the moment, one's one side of the Sun, the other's the other side. Now, once it passes through its inferior conjunction, the bright part of Mercury will start to appear on the same side as Venus. Venus is still there. It's faster than us, so it's moving away from us. It's getting away a little bit, and so it's not quite as large as it has been in the last few months. Mars, on the other hand, we're actually catching Mars. So eventually, towards about October, we'll move between the Sun and Mars, which will put Mars into opposition. So Mars itself is only going to get bigger. Saturn, as I said, you can still see the rings, but if you think back to last year, remember this picture, which I bet you can't, the rings are actually closing. And as I said, in 2025, they'll be edge on. And it's just effectively like a gyroscope, and as it moves around the sun's here, as it moves around we can see the rings, but as the rings move to there, and we pass between them, we won't be able to see the rings. And what known as we're passing through the ring plane. Jupiter, always spectacular to look at. Always gives a good show even in an average size telescope. Things you're obviously looking for are the bands and the red spot. Sometimes it's quite clear, other times it's not quite as red as you'd like it to be. Uranus and Neptune, I reckon that if they were that size, you're looking at them through a fairly decent sized telescope. No, 5th of May, Uranus is in conjunction. Won't see it. We've got 3 comets. Got Pan stars, which is brightening from about 9 to 8 magnitude, so it's about as bright as Neptune. So obviously a telescope object, but that's fairly bright for a comet. It's around about 2 AM in Aquila. We'll move into Ophiuchus, which is next to Scorpio, between Scorpio and Capricorn, on the equatorial plane, and we'll stay there for most of August. There's Ophiuchus in Sagittarius, it might be Scorpio and Sagittarius, we'll come there somewhere. Comet Kopf in Aquarius for the month before moving into Pisces. It rises at about 2 AM as well, so it's a real morning time for the team. It's about 11.5 magnitude, and it has a fairly close encounter with Mars and Neptune on the 21st of this month. So I'll get a picture of that. The blue planet, a red planet, and a comet. And the new one just recently found, so they're not 100% certain how it's going. I reckon it'll be around about 11th magnitude, found in Guru, Cygnus, Tucana and Octans, which means it's in the vicinity of our South Pole. So in a fairly good spot for us to have a look at, try and chase down. That's there. Hopefully it gets a bit brighter. Apparently it's in there, so it may get brighter. And meteor showers this month. The Eager Aquarians, which have actually been in progress. Unfortunately, the peak was earlier this month, but it's associated with Halley's Comet, and apparently it still gives off quite a few meteors up until about the 28th of this month. Best viewed in the morning, and obviously look towards Aquarius. And as usual, nice information provided by Astronomy 2022, Wallace Stores and Northfield. Any questions?
Okay, well I've got 2 videos. Each of them goes for about 15-20 minutes at most, all about the Sagittarius A star black hole. And one thing that actually confuses quite a lot of people is the name given to the black hole. So the original discoverer back in 1974 called it Sagittarius A. But the actual star on the end, or the asterisk on the end of it, the origin of that is pretty obscure. No one is actually officially sort of written down anywhere as to why is it A star rather than just A, because the original paper, which I looked up, just says Sagittarius A, and it's thought that around Sagittarius A there are actually 3 radio sources very, very close together, and the most energetic one is actually Sagittarius A star. So it's thought that the asterisk was put on the one of those 3 radio sources that was the most energetic in radio waves. But other than that, that's the only reason I can find.
Alright, there is so much to unpack with this new image of the Milky Way's supermassive black hole. Like, why is it orange, and why is it so blurry, and what are the 3 blobs, and how does it compare to the first ever image of a black hole we had in Messier 87 as well, and what angle are we even viewing this from? So, Let's dive into this. Yesterday, on the 12th of May 2022, the Event Horizon Telescope released this image of the supermassive black hole at the center of our galaxy, the Milky Way. It's known as Sagittarius A star because the center of the galaxy is in the same direction as the constellation Sagittarius on the sky. And in the past, zooming into that region of the sky, all we've ever seen is this unresolved blurry blob. But now, the material orbiting close into the black hole has finally been resolved with all of this detail. You can see this bright ring of radio light from the material orbiting the black hole, and you can see the shadow of the black hole where we're no longer receiving any lights. To get an image like that, zooming in that far, you need a really big telescope. And the Event Horizon Telescope essentially combines a whole bunch of telescopes around the Earth to create effectively a telescope that is the size of the Earth. Because the bigger the telescope, the smaller the thing you can see on the sky, the more you can zoom in. Because even though the Milky Way supermassive black hole is 4 million times the mass of the sun, the actual diameter or the size of the event horizon, that region that we're no longer getting any light from, appears to be about the size of Mercury's orbit, 116 million kilometers across. Which sounds big, but the center of the Milky Way is also 27,000 light years away from us. So it took light traveling at 300 million meters a second, 27,000 years to get from there to here. And so it actually appears really small on the sky. If you think of the sky of being 360 degrees all the way around, then this thing only spans a distance of 0.0000001 degrees. Now, this thing looks like a big orange donut, right? This big ring of material. And so the best analogy I've heard to describe, how small that would actually appear is it would be like seeing a donut on the surface of the moon. But also, this thing is only about 100 times brighter than the sun, which might sound bright, but that's pretty faint for material spiraling around a black hole. And combine that with the distance it's at, it's even fainter still. So to actually detect this, you have to combine lots of different telescopes from around the world in a process known as interferometry. You can think of this as if the Earth is a disco ball, with each bit of mirror of the disco ball a telescope looking up at the sky to see this one big image. Now, unfortunately, we don't have a telescope at each of these locations on Earth, though there are gaps in the disco ball of this array of telescopes. But as the Earth rotates, this then fills in some of the gaps in the picture. But as you can see, it's not all the gaps that get filled in. So the collaboration at the Event Horizon Telescope actually had to develop this brand new computer algorithm, a machine learning algorithm that could fill in the gaps using images that we've seen before of other completely different things to find the most likely image of what it would like given the bits of data that we do have. Katie Bullman, who's a computer scientist on the Event Horizon collaboration team, has given a great TED talk on this before if you want to know more about how this algorithm actually works. I'll link it in the video description down below. Now, this was the exact same process as was used to image the supermassive black hole in the center of the galaxy Messier 87. Now, the observations of both M87 star and Sagittarius A star were done with the Event Horizon Telescope around about the same time, in April and November of 2017. But it was the image of M87's black hole that was released first way back in 2019, and that surprised a lot of people because I think people thought that we'd get the image of Sagittarius A star first since it is the closest of the two black holes to us. But the thing is, Messier 87's black hole is 1,000 times more massive than the Milky Way's black hole, which means that its diameter, its event horizon, is also 1,000 times bigger. But get this, M87's black hole is 1,000 times further away from us than Sagittarius A star is, which means they actually appear roughly the same size on the sky. In the same way that the moon is roughly 400 times smaller than the sun, but it's 400 times closer to Earth, so it appears the same size in the sky, and this is why we can actually see total solar eclipses where the moon fully blocks the sun. So when we compare these two images side by side, we have to remember that in reality, Sagittarius A star is way, way smaller than M87 star. And while the whole solar system can fit inside the black hole shadow of M87 star, not even the orbit of Mercury fits inside the black hole shadow of Sagittarius A star. And yet the two images look remarkably similar. So what that tells us is that despite these two black holes being in two completely different types of galaxies with two completely different galaxy masses, is that up close to the event horizon, they behave in exactly the same way. So any differences that we see far away from the black hole, like for example the M87 has these huge jets that are launched from the surrounding regions of the black hole, that's all to do with the material that the galaxy pumps into those regions around the black hole, not the properties of the black hole itself, which is a really cool result and has really big implications for just galaxy evolution as a whole, and especially my research where I look at this co-evolution of galaxies and their supermassive black holes together. Now, the other thing you might have noticed comparing these two is that the Sagittarius A star image is a lot blurrier than the M87 star image. And that actually comes down to the fact that these things are actually quite faint by the time the light reaches us. So to collect enough light to build up an image, we actually have to observe them for a really long time, like hours at a time in a single night. But the material that's orbiting and looping around the black hole that's glowing and giving off that radio light that we actually detect is moving close to the speed of light. And so it loops around the fairly small Sagittarius A star in just a couple of minutes, which means that as you stare at it for hours, it's constantly changing and you essentially get like movement blur on your image. Whereas M87's black hole is 1,000 times wider, and so even though the material is moving at close to the speed of light, it takes a couple of weeks to fully orbit that black hole, which means that as you stare at it for a number of hours, material doesn't look to actually move that much, and so you get a much crisper, clearer, static image. So that meant it was much easier to analyze and construct that image of M87 star from the data that they had because it was static, whereas for Sagittarius A star, they had to develop this new sophisticated computer algorithm that could actually account for the movement blur in the image. The other problem is that when we look towards M87, we're looking up and out of the galaxy, and there's nothing really in our way spoiling the view. Whereas when we look towards the center of our galaxy, we're actually looking through a huge amount of dust and ionized gas, all of which has an effect on the light heading our way. For example, optical light gets completely absorbed by dust, which is why you see these darker patches in the sky at night in the Milky Way. But radio light actually gets scattered by free electrons in gas that's between us on Earth and the center of the Milky Way, which means that light from this already very faint object, we're losing some of it thanks to the scattering, but also some of it will have just changed direction slightly as well. So it'll appear as if it's come from one part of this ring of light around the black hole, but actually it's come from a slightly different part. It's just been scattered to look like it's come from a different direction. So that, combined with the fact that your image isn't static, you've got all of this movement happening all the time, made analyzing, constructing this image so much more difficult. 3 extra years in a pandemic, difficult. Now, I also asked on a YouTube community post and on my Instagram stories yesterday what questions you all had after seeing this image. You know, the kind of things that you still didn't understand that me looking at it with an expert eye would almost take for granted that was known, but actually that wasn't obvious at all. So the first of those was quite simply, why is it orange? So this is a false color image, right? We're not recording like orange visible light that we could actually detect and see with our eyes. The telescope is recording radio light. What it's essentially doing is saying, okay, where is there and where isn't there light in this region of sky? So the raw image is essentially like black and white. The problem is showing this image in black and white, the human eye actually isn't very good at picking out detail in a grayscale image. Like, it can't detect the difference between a bright region and a really bright region when you're just going from black to white. So they use a different color scheme essentially to show off this image. Now, you could literally use anything to represent the intensity of the light changing, right? You could use a rainbow, you could use red to blue, or this sort of black through orange through white color scheme that they've used here, which has sort of been the default, like the mainstay for a number of years now for any astronomical image that's taken at wavelengths longer than red visible light. So the wavelengths that are longer than we can actually detect with our eye, the likes of the infrared, the submillimeter, and radio light like this image here. It's also why James Webb Space Telescope images also have this similar orangey color scheme as well. They're also false color because they're taken in the infrared. The second question a lot of you had was, what are the 3 blobs? And why is there only 1 blob in the M87 image, but there's 3 of them in the Sagittarius A star image? All right, so the blobs are what are known as hotspots, essentially where you've got these big clumps of gas in this ring of material that's orbiting around the black hole, that because there's more material there in this big clump, they will glow brighter. But if you remember, the material that's orbiting around Sagittarius A star is doing so at incredible speeds, and it only takes, less than half an hour or so to go around. So if you observe it for a number of hours, every single night in a row for 3 nights, the location of that hotspot is going to change, so that when you average all the light that you've collected, you average all of those images, you're going to see it a number of times. You can tell though that one of the blobs in the Sagittarius A star is brighter though, and this is due to something known as Doppler beaming. Essentially, the light is brighter where the material is coming towards you as it spirals around the black hole. Think about a lighthouse beam, for example. Think about how bright it appears when it's pointing in a different direction, and then how bright it is when it sweeps around to point directly at you. It's pretty much the same thing here, except the effect is exacerbated by the fact that you've also got the material moving at close to the speed of light as well, so it makes that beaming that much stronger. But what it allows us to do is essentially work out, well, how is the material moving around this black hole? So for M87 star, it's likely that material is moving towards us like this, whereas for Sagittarius A star, it's likely the material is looping around the black hole like this. The third question I saw a lot of you asking was, what angle are we actually viewing this from? So the event horizon of a black hole is a sphere, right? Because we started with either a star that was a sphere or a big clump of gas that was a sphere, right? And we've collapsed it down till it's dense enough that we can no longer get any light from us, and that event horizon marks that point, which is a sphere, which means that we look at it from all the different directions, it's going to look exactly the same. But the thing is, it's also spinning, which means any material that comes into that black hole is essentially going to get flattened out into a big disk that we call an accretion disk. In the same way that if you take a ball of pizza dough and throw it above your head, it will flatten out into a nice pizza-based disk shape. So even though the black hole being like spherically symmetric, the same from all angles, the accretion disk, right, will have this flat plane that you can either see edge on or you can see face on. So you would think that it would look slightly different depending on what angle that you viewed it from. The thing is, because the black hole plays tricks on you because of the way that it bends light around it, we actually see almost the same view no matter what angle we look at this big disk of material around the black hole from. Almost, anyway, because one thing that does change is the locations of where that blob of material is the brightest that's coming towards you that gets Doppler beamed. Now, I know a lot of people thought that we'd be seeing this edge on because they assumed that, well, the axis that the black hole is rotating around and the axis that the Milky Way is all rotating around would be completely perfectly aligned. But in fact, we don't expect that at all. In the majority of studies that have been done on this, that have looked at sort of the spin axes of black holes versus galaxies, we actually find that they're completely misaligned, at least in the areas that we can get at this information. So usually we find this from the fact that the regions around the black hole, that material has been funneled into jets that have essentially come out of like the north and south pole of the black hole. And then you can figure out, okay, well, how is the black hole rotating? And we think that's because if you have a galaxy merger where both of those galaxies have a supermassive black hole at the center, eventually those two supermassive black holes will merge. And if they've come in at different angles, then essentially you will sort of average out the two different axes that they're spinning around, and you'll get something that's misaligned with the galaxy that's left over. Now, we have some idea over the axis around which M87 star is spinning, because M87 has these huge big jets coming out of it. And that's actually really helpful to know because it makes filling in those gaps where you don't have the data covering the entire image that much easier if you know what angle that you're looking at it from. The thing is, we don't know what angle we're looking at the Milky Way's black hole from because it's nowhere near as active as Messier 87's black hole. It's nowhere near taking in as much as material, which is why it's a lot fainter as well. Again, because we didn't know that angle, it's another reason why the image of Sagittarius A star is a lot more blurry than M87 star's final image. But the final image that we do end up with of Sagittarius A star is actually still really useful to help us constrain, okay, what angle are we actually looking at this from? You know, from the location of the blobs and which one's the bright one and how is the gas moving with respect to us. It can help us rule out certain scenarios. So the Event Horizon collaboration team, in all the papers that they published along with this image as well, essentially ruled out that we are looking at the disk edge on at 90 degrees. In fact, they actually managed to put a limit on it, saying that we have to be looking at it with an inclination of less than 50 degrees to us. And actually the most likely model has an inclination of about 30 degrees to our line of sight looking directly at the black hole. So essentially the black hole is spinning at around about 60 degrees relative to the axis that the Milky Way is spinning around. Now, even though by studying other galaxies we've seen that you can get all sorts of different alignments of galaxy spin and black hole spin, there still was sort of an assumption that in the Milky Way, the black hole spin and the galaxy spin would be aligned. And that's because of something known as the Fermi bubbles. We're not 100% sure what these are, but the best hypothesis is that they are echoes of essentially a big black hole burp that Sagittarius A star gave off at some point in the past. And from where we observed them in the sky, we figured out that they are perfectly above and below the Milky Way's disk, suggesting that when it was given off in this burp from the black hole regions, the black hole was aligned with the Milky Way's spin axis. So has it changed since then? So then you start thinking about ideas, well, okay, maybe the Milky Way has had a galaxy merger in the past, and that means that the black hole has recently merged, which perhaps changed the axis that it rotates at. Or are we thinking about the Fermi bubbles wrong? Perhaps instead of being sort of above and below being expelled from the top, maybe it was expelled spherically, but the only reason we see them is where they sort of escape the galaxy disk, which is above and below. So there's loads of questions been raised by this inclination and figuring out what angle we're seeing Sagittarius A star from. So not only does this image prove that at the center of the Milky Way is a supermassive black hole 4 million times the mass of the sun, you know, rather than like a swarm of lots of smaller black holes or just like a clump of dark matter, as some people were suggesting in the past couple of years as well. It also lets us delve into the history of the Milky Way and the history of the Milky Way supermassive black hole as well, and sort of ask questions about how the two have co-evolved, grown up together over billions of years. And finally, you all wanted to know whether we can also look at this with the James Webb Space Telescope. Yes, there are plans to look at the galactic center with JWST. I actually talked about this in my last video listing my top 5 targets for the James Webb Space Telescope if you want to check that out. But JWST will not be able to see this. It'll just be a blob. It's too small for Webb to resolve. Webb is much smaller than the EHT, right? It's only 6.5 meters across rather than the size of the whole Earth. The smallest thing that JWST can see on the sky is 0.00006 degrees, whereas the size of that glowing ring of light in the EHT image is 300 times smaller than that. Instead, JWST can peer through all the dust towards the center of the galaxy and reveal the stars orbiting around the supermassive black hole, and also any gas that's orbiting around the supermassive black hole just further out from the stuff that we're seeing in the EHT image. The proposal to do this was successful, so this is definitely going to be observed in James Webb's first year, and these observations will allow us to answer questions like, how old are all the stars in orbit around the black hole, and did they form there? Have they been affected by being so close to the black hole? Like, have they had their outer layers stripped? Is there actually maybe a collection of smaller black holes just orbiting around the supermassive black hole as well? Or maybe even like a big clump of dark matter that's stuck in orbit around the black hole as well? And once again, test predictions of Einstein's theory of general relativity, i.e. do we understand how gravity works, to extreme precision, more than we were ever able to do, for example, with the Keck telescopes, which is what Andrea Getz and Reinhard Genzel won the Nobel Prize for back in 2020. In the same way, the Event Horizon Telescope collaboration were able to test with their image whether the gas was moving very, very close into the black hole, again, how we'd expect given what general relativity tells us. And they found that just like with M87, the gas is moving just as we'd expect. So once again, us astrophysicists find ourselves saying that even 100 years later, Einstein was right. Again.
This is a picture of the supermassive black hole at the center of our Milky Way galaxy, known as Sagittarius A star. The black hole itself doesn't emit light, so what we're seeing is the hot plasma swirling around it. This is only the second picture of a black hole ever. It was taken by the Event Horizon Telescope collaboration, the same people who brought you this image of the supermassive black hole at the center of galaxy M87. Now, their original plan was to image Sagittarius A star first. Since it's in our own galaxy, it is 2,000 times closer than M87 star. But it's also over 1,000 times smaller. So from Earth, it appears only slightly larger than M87 star. And there are a number of additional challenges to observing it. First of all, there is a lot of dust and gas between us and the center of our galaxy, so you can't even see it with visible light. In this video from the European Southern Observatory, we zoom in on our galaxy's core. As we get closer and closer, at some point we have to switch over to infrared light, which can better penetrate the debris, allowing us to see it from Earth. Over the past 3 decades, we've been able to peer into the heart of the Milky Way and witness something truly amazing. A collection of stars zipping around on all kinds of eccentric orbits. They go incredibly fast. One of the stars was clocked going 24 million meters per second. That's 8% the speed of light. All these stars appear to be orbiting something incredibly massive and compact. But this object isn't glowing brightly like a star. If you watch closely, you can see it flicker now and then. This is what we believe to be a supermassive black hole. From the motion of the stars around it, we can infer that the black hole's mass is about 4 million times that of our sun, but all crammed down into a tiny point, the singularity. Anything, including light, that comes within a Schwarzschild radius of this point can't escape and ends up in the singularity. So for us to see any radiation from the black hole, it must come from further out than this, usually from superheated plasma as it falls in. But for its size, Sagittarius A star doesn't consume much matter. It's unusually quiet and dark. The supermassive black hole at the center of M87, in contrast, is much more active, gobbling up matter from its accretion disk. Plus, since it's over 1,000 times bigger, it takes 1,000 times longer for objects to orbit it. And that means, from Earth, its appearance over time is more consistent, in contrast to Sagittarius A star, where things can change on the order of minutes. These visualizations are from Luciano Rizzola and colleagues at Goethe University Frankfurt. But the biggest challenge of all in making an image of either supermassive black hole is that these objects are so compact and so far from Earth, in the sky they appear very, very tiny. To get a sense of just how tiny, take the whole sky and divide it into 180 degrees. The Andromeda galaxy spans about 3 degrees. Then divide 1 degree into 60 arc minutes. And 1 arc minute into 60 arc seconds. Divide an arc second into 100. Into 100 again. And into 100 once more. And this is the size of the black holes on the sky. It's equivalent to taking a picture of a donut on the moon. Now, there is no optical telescope on Earth that could produce such an image. So in this video, I want to answer 2 questions. How did they do it? And what are we actually looking at? So starting with, how did they make these images of black holes? Well, the first thing to know is they weren't made with visible light. They were made using radio waves with a wavelength of 1.3 millimeters. So all the observations were taken by radio telescopes, which essentially look like huge satellite dishes. When a source emits radio waves, they travel out radially in all directions. But Earth is so far away that by the time they reach our planet, the wavefronts are almost completely flat and parallel. This is known as a plane wave. A radio telescope works by scanning back and forth across the sky. When it is pointed directly at a radio source, it produces a bright spot. That's because all the radio waves travel the same distance, bounce off the dish, and are received at the same time. So they are in phase, meaning peaks line up with peaks and troughs with troughs. They constructively interfere. As the telescope moves past the source, some of the radio waves now travel farther than others, and therefore they meet up out of phase, destructively interfere, and the intensity of the signal drops to 0. To make a sharp image, you want this drop-off to be as steep as possible. So the telescope produces peak intensity only when aimed directly at the source, and then the intensity drops rapidly when the dish is moved just a tiny bit in any direction. There are 2 ways of achieving this. One is to observe higher frequency radio waves. That way, any slight movement of the telescope represents a greater fraction of a wavelength. This causes destructive interference to occur sooner. The other way is to increase the diameter of the telescope. This increases the difference in path length between radio waves on opposite sides of the telescope for a given angular adjustment. How narrowly a telescope can identify the source of radio waves is known as its angular resolution. You can think of it as the size of the spot on the sky that the telescope is sensitive to. It is proportional to wavelength and inversely proportional to the diameter of the telescope. The challenge with making a picture of a black hole is that you're trying to see the structure in a tiny area of the sky. Imagine scanning a radio telescope across the center of a black hole. You would want to see the bright spot as the telescope passes over the left edge, and then a dark spot, and then another bright spot as it passes the right edge. The problem is, for any individual radio telescope on Earth, the angular resolution is too large. So as it passes over the black hole, it would still be receiving radio waves from the left side as it begins receiving radio waves from the right side. The resolution isn't high enough to tell if there's a ring structure there, as we'd expect with a black hole, or if it's just a blob. Observing at shorter wavelengths isn't really an option, because that light is blocked either by our atmosphere or by the matter around the black hole. So if you want to improve resolution, the only way you can do it is by increasing the diameter of the telescope. But if you actually do the calculation, you find that the telescope you'd need would have to be the size of the Earth in order to see the ring of a black hole, which is obviously impossible. But there is a way to do something that's almost as good. You don't need a complete dish the size of the Earth, just pieces of it, individual radio telescopes that are separated by distances up to the Earth's diameter. As long as you can properly combine the signals from all these distant telescopes, you get the constructive and destructive interference required to achieve the same angular resolution as an Earth-sized dish. This technique is called very long baseline interferometry. So the Event Horizon Telescope is not just one telescope, but a global network of radio observatories. All these telescopes observe Sagittarius A star at the same time. Unlike a single telescope, you can't bounce all the radio waves to a central receiver and add them up in real time. So instead, each telescope records the signal at its location and the exact time down to the femtosecond. Petabytes of data are generated. But now that data needs to be brought together. And the fastest way to do it was actually to carry hard drives as hand luggage to centralized locations. Now, think about the data we've got. Electrical signals and precise timings from a number of radio telescopes around the world. But none of those radio telescopes has enough angular resolution to see the ring of the black hole. So how do you combine that data and get finer detail than any of the inputs? Well, there is additional information in the relative distances between these telescopes and in the time delays between when a wavefront hits one telescope relative to the others. Imagine combining the signals from two distant telescopes. Let's say they both received the same wave at the same time, so those waves were coming in phase. Well, then the source must have been located directly between them. The radio waves would have traveled the same distance to each telescope to arrive at the same time. Except with just two telescopes, that only narrows it down to a line in the sky that is equidistant from both telescopes. The source could have been anywhere on that line. And it's actually worse than that. It's possible that the source could be exactly one wavelength closer to one of the telescopes, and that way the radio waves would still arrive perfectly in phase. Or the difference could be 2 or 3 or 4 wavelengths, but you get the point. So from one pair of telescopes, the information we get about the source is actually a series of bright and dark fringes. Telescopes that are close together produce wide fringes, while those that are far apart produce narrow fringes. So to make an image, you need pairs of telescopes at all different orientations and different distances apart. Each pair makes a different interference pattern. And then by combining all these patterns, we get an image of the black hole which created them. But now that we have this picture, what exactly is it showing us? Well, this is how I explained it when the first image of a black hole was released. So here is my mock black hole of science. And this sphere represents the event horizon. Once you're inside here, there's no coming back, not even for light. The radius of the event horizon is known as the Schwarzschild radius. Now, if we were just to look at a black hole with nothing around it, we would not be able to make an image like this because, well, it would just absorb all electromagnetic radiation that falls on it. But the black hole that they're looking at has matter around it in an accretion disk. In this accretion disk, there is dust and gas swirling around here very chaotically. It's incredibly hot. We're talking millions of degrees, and it's going really fast, a significant fraction of the speed of light. And it's this matter that the black hole feeds off and gets bigger and bigger over time. But you'll notice that the accretion disk does not extend all the way into the event horizon. Why is that? Well, that's because there is an innermost stable circular orbit. And for matter around a non-spinning black hole, that orbit is at 3 Schwarzschild radii. Now, in all likelihood, the black hole at the center of our galaxy will be spinning, but for simplicity, I'm just considering the non-spinning case. You can see my video on spinning black holes if you want to find out more about that. So this is the innermost orbit for matter going around the black hole. If it goes inside this orbit, it very quickly goes into the center of the black hole and we never hear from it again. But there is something that can orbit closer to the black hole, and that is light. Because light has no mass, it can actually orbit at 1.5 Schwarzschild radii. Now here I'm representing it with a ring, but really this could be in any orientation. So it's a sphere of photon orbits. And if you were standing there, of course you could never go there, but if you could look forward and actually see the back of your head, because the photons could go around and complete that orbit. Now the photon sphere is an unstable orbit, meaning eventually either the photons have to spiral into the singularity or spiral out and head off to infinity. Now the question I want to answer is, what does this black quote-unquote shadow in the image correspond to in this picture of what's actually going on around the black hole? Is it the event horizon? Are we simply looking at this? Or is it the photon sphere or the innermost stable circular orbit? Well, things are complicated. And the reason is this black hole warps space-time around it, which changes the path of light rays. So they don't just go in straight lines like we normally imagine that they do. I mean, they are going in straight lines, but space-time's curved, so yeah, they go in curves. So the best way to think of this is maybe to imagine parallel light rays coming in from the observer and striking this geometry here. Of course, if the parallel light rays cross the event horizon, we'll never see them again, so they're gone. That will definitely be a dark region. But if a light ray comes in just above the event horizon, it too will get bent and end up crossing the event horizon. It ends up in the black hole. Even a light ray coming in the same distance away as the photon sphere will end up getting warped into the black hole and curving across the event horizon. So in order for you to get a parallel ray which does not end up in the black hole, you actually have to go out 2.6 radii away. If a light ray comes in 2.6 Schwarzschild radii away, it will just graze the photon sphere at its closest approach, and then it will go off to infinity. And so the resulting shadow that we get looks like this. It is 2.6 times bigger than the event horizon. And you say, what are we really looking at here? What is this shadow? Well, in the center of it is the event horizon. It maps pretty cleanly onto the center of this shadow. But if you think about it, light rays going above or below also end up crossing the event horizon just on the back side. So in fact, what we get is the whole back side of the event horizon mapped onto a ring on this shadow. So looking from our one point in space at the black hole, we actually get to see the entirety of the black hole's event horizon. I mean, maybe it's silly to talk about seeing it because it's completely black, but that really is where the points would map to on this shadow. It gets weirder than that. Because the light can come in and go around the back and say get absorbed in the front, you get another image of the entire horizon next to that, and another annular ring, and then another one after that, and another one after that, and you get basically infinite images of the event horizon as you approach the edge of this shadow. So what is the first light that we can see? It is those light rays that come in at just such an angle that they graze the photon sphere and then end up at our telescopes. And they produce a shadow which is 2.6 times the size of the event horizon. So this is roughly what we'd see if we happen to be looking perpendicular to the accretion disk. But more likely, we will be looking at some sort of random angle to the accretion disk. We may be even looking edge on. And in that case, do we see this shadow of the black hole? You might think that we wouldn't. But the truth is, because of the way the black hole warps space-time and bends light rays, we actually see the back of the accretion disk. The way it works is light rays coming off the accretion disk bend over the top and end up coming to our telescopes. So what we end up seeing is something that looks like that. Similarly, light from the bottom of the accretion disk comes underneath, gets bent underneath the black hole, and comes towards us like that. And this is where we get an image that looks something like the interstellar black hole. It gets even crazier than this, because light that comes off the top of the accretion disk here can go around the back of the black hole, graze the photon sphere, and come out the bottom right here, producing a very thin ring underneath the shadow. Similarly, light from underneath the accretion disk in the front can go underneath and around the back and come out over the top, which is why we see this ring of light here. This is what we could see if we were very close to the black hole, something that looks truly spectacular. One other really important effect to consider is that the matter in this accretion disk is going very fast, close to the speed of light, and so if it's coming towards us, it's going to look much brighter than if it's going away. That's called relativistic beaming or Doppler beaming. And so one side of this accretion disk is going to look much brighter than the other, and that's why we're going to see a bright spot in our image. So hopefully this gives you an idea of what we're really looking at when we look at an image of a black hole.
And with that, I will just close with this image, this video that goes for about three minutes or so from the National Science Foundation about Sagittarius A as well. We live in exciting times. Thank you very much for coming to May's meeting, and we'll see you all next month at the June meeting.
Thank you, Peter. Thank you.